Hello everybody, welcome back to Physics 425. In the last video we were talking about the conduction of heat through solids, and we did a couple of things. One of them was to establish an analogy between electrical circuits and thermal circuits, and we could use that type of analysis to determine how the temperature of an object changed with time. The other thing we did is we derived the 1D heat equation, which I've written down here. It's a second order partial differential equation, and alpha is the thermal diffusivity. We didn't do anything with this 1D heat equation in the last video, and so what I want to do today is to consider a particular experimental geometry and solve it. And we're going to do it for a couple reasons. One is that it's satisfying to just solve a problem from start to finish. Second, it will show that we can have what seems like a very simple experimental setup and find that it leads to a pretty complicated solution. And third, it will also show that when we can, it will be to our advantage to use the thermal circuit analogy because it's much easier to analyze than always having to solve a complicated differential equation. So here is the scenario we're going to consider. We're going to assume that we initially have a bar, a solid piece of metal or something. It's a rod, and it's at a uniform temperature. So what we'll do is we'll anchor one end of the bar to a thermal reservoir, and we'll make that thermal reservoir a temperature T0. And so that T0 of the reservoir is never going to change temperature. We'll say this end of the bar is at a position x equals L, and this end is at x equals 0. So the bar has a total length L. Okay, so initially we have just T0 everywhere. Then the temperature is changed suddenly to T1 at x equals 0. And so maybe there's a heater or something connected to the top of the bar, and at some point we turn on that heater, and so at x equals 0 the temperature is suddenly T1. While that happens, at x equals L, the temperature remains fixed at T0. What we're going to try to do is we're going to try to use this 1D heat equation to figure out what the temperature at all different points x along the bar is at all possible times. Okay, so here if we were to plot as a function of time the temperature at x equals 0, what it would look like is initially it's at T0 because the bar was at a uniform temperature when we started, and then at some particular time it's going to suddenly step up to T1. We'll call that time t equals 0, and so here is t equals 0. Okay, what we're going to do is we're going to make a change of variables. So we're going to define u to be t minus t naught, so that t is u plus t naught. Our 1D heat equation involves a time derivative of temperature, but because t naught's a constant, the time derivative of t is equivalent to the time derivative of u, And our heat equation involves two position derivatives of temperature. And again, T naught's a constant, so that's equivalent to two position derivatives of U. Okay, the other thing we're going to do is we're going to define alpha to be c squared. And when we make those changes, our heat equation becomes du dt is equal alpha, which is c squared, d2u dx2. All right, so we're going to have to do some integration, and for example, we're going to integrate with respect to time, and that's going to lead to an initial condition, which will be used to solve for some integration constants. Initial condition. And then we have to do two spatial derivatives, and we're going to require boundary conditions to find those integration constants. Okay, and so let's just state what they are. The initial condition for temperature at T equals 0 or all times before T equals 0 is that the bar is at a uniform temperature T naught. Because U is defined to be temperature minus T naught, that means U is equal to 0 for all x when T is less than 0. Okay. One of our boundary conditions is that at x equals L, our rod is connected to the thermal reservoir, and so its temperature is T naught. U is T minus T naught again, so that just means that at x equals L, U is equal to 0 for all times. And then finally, we have at x equals 0, for times greater than 0, the temperature of the rod is T1. So that's where we have the step in temperature. And so that means U at x equals 0 for times greater than 0 is equal to T1 minus T naught. And so this is T greater than 0. Okay, and so we're going to make use of these conditions as we come up with our solutions to the differential equation. Okay, the method we're going to use is separation of variables, and no doubt you've seen this before. So what we're going to say is we're going to say U, which is a function of position and time. Let's suppose that we could write that as a function of x times some other function of time. Okay. Then du dt, f has no time dependence, so we're just going to get f times the time derivative of g, which is g dot. And d2u dx2, g has no position dependence, and so we just get two derivatives of f, which we'll indicate as f double prime, and then we multiply by g. Okay, so if we substitute this into our heat equation, we have du dt, which is f g dot is equal to c squared times two derivatives of u with respect to x, and so that's f double prime g. Okay, next what we're going to try to do is we're going to put all of the time dependence on one side and all of the position dependence on the other side, and we'll do that by dividing by c squared f g. Okay, on the left hand side, when we do that, the f cancels, and so we get g dot over c squared g is equal to, on the right hand side, c squared and g cancel, So we get f double prime over f. And so now what we have is, on one side, a function of t. On another side, we have a function of x. And the only way that these two functions can always be equal to each other at all times and all positions is if these ratios are equal to some constant. And so we'll call that constant h. Okay. We can use this to establish two homogeneous ordinary differential equations. First, let's deal with the f. So we have f double prime over f is equal to h, or equivalently, f double prime minus h times f is equal to 0. And so the homogeneous part means that we have some stuff involving f and its derivatives equal to 0. Okay, the other one is, let's see, g prime minus hc squared g is equal to 0. So we've managed to convert our second order partial differential equation, which depended on both position and time, into two separate differential equations. One depends on only position and the other depends only on time. So we're going to start with equation 1. And in equation 1, h is a constant, but there's no real restrictions on that constant, so there's going to be a bunch of cases to consider. The cases are going to be that h is a positive constant, h is 0, and h is a negative constant. And we'll have to think about those three cases separately. So we're going to start with h is mu squared, which is something that's positive, greater than 0. So as long as mu is a real valued quantity, then mu squared has to be positive. So what we have then is that f double prime minus mu squared f is equal to 0. And the solution is f of x is equal to a e mu x plus b e to the minus mu x. And so you could just check that just by taking the two derivatives and just making sure that this equality holds. Okay, now let's try some of our boundary conditions. Or in fact, I guess this is really, let's say, our initial condition. At t equals 0. And remember what that was is that for times less than 0, no matter what the position was, u had to be equal to 0. So in particular, we could say at x equals 0 and t equals 0, u must be 0. And at x equals L and t equals 0, u must be equal to 0. Okay, so let's start with the first one. Both position and time are equal to 0. So we'll go to our solution over here, and we'll just put in x equals 0. And so that's going to be f x equals 0. And then remember, u is f times g, and g is a function of t, but t is equal to 0, so we have this g0. And so when we put in x equals 0 for our f solution, we get e to the mu times 0, which is 1, and an e to the minus mu times 0, which is 1. And so the f just becomes a plus b. And then we have g at t equals 0 And all of this has to be 0, right? Because that was our boundary condition. We don't want to have to assume that g of 0 is 0, right? We haven't solved that differential equation. We don't know what the solution is going to be. So what we're going to require is that a plus b is equal to 0, or b is equal to minus a. Okay, and then we do the second boundary condition at x equals L. And so f of x becomes f of L, and we still have g of 0. And f of L, so we're going to have a e to the mu L plus b e to the minus mu L times g of 0. And again, that has to be equal to 0 because that was the boundary condition. But we already know that b is minus a, and so what we get is a e to the mu L minus e to the minus mu L, g of 0 has to be 0. Okay, but we assume mu is some positive number, so mu is not equal to 0. We're going to consider the case h equals 0, and therefore mu equals 0 later. And we don't want to set g equal to 0, and so that must mean, therefore, a is equal to 0. But b is minus a, and so minus 0 is 0. So in this case, where h is positive, the solution for f is equal to 0. That's kind of nice, because that's one case that we don't have to worry about then. The next case we'll look at is h is equal to 0. So remember, our first differential equation is f double prime minus h times f is equal to 0. But if h is 0, then what we're trying to solve is f double prime is equal to 0. The solution is a straight line, and you could probably see that pretty easily, because if we write f is a straight line, some slope times x plus b, when you take the first derivative, that's just equal to a, the slope, and then when you take the second derivative, if you have a straight line, the slope is a constant, and f double prime equals 0, and that's as expected. Okay, so now we have the constants little a and b, and we need to use our boundary conditions to find their values. Okay, so one of the boundary conditions is that at x equals 0, for t greater than 0, the temperature was T1, and so U is T1 minus T0. This is for t greater than 0. So that means that f of x, or f of 0, times g of t is equal to T1 minus T0. Okay, but f of 0, if we put x equals 0 into our solution, is just b. And so our boundary condition tells us that b times g of t is equal to T1 minus T0. Okay, so the other boundary condition is at x equals L, at x equals L, we have f at x equals L times g of t has to be equal to 0, because at x equals L, the temperature is T naught, and U is T minus T naught, which is 0 in this case. Okay, so then we go back to our solution, and we're going to say x equals L, so that we get A times L plus B. So A, L plus B times G of T is equal to 0, or A, L, G of T plus B, G of T is equal to 0. But if you look over here, we've already established that B times G is T1 minus T naught. And so this is going to be T1 minus T naught, which we can then solve for A. A is equal to minus T1 minus T naught over L times G of T. Okay, so far we don't know what G of T is. However, we can note the following. Note that since the second differential equation, which we haven't considered yet, was this form: G dot minus hc squared times G is equal to 0. And we're considering right now the h equals 0 case. So if we set h equals 0, we just get G dot is equal to 0. Or G is a constant. What we're going to do is we're going to arbitrarily set G equal to 1 for the h equals 0 case. So we can arbitrarily set G of T equal to 1. The reason we can do this is because we're going to have other integration constants which are going to set the overall scale of U. So if we choose now to say G of T is equal to 1 for the h equals 0 case, then B is going to be equal to, so where is it? B times G was T1 minus T naught, but G is 1. So B is now T1 minus T naught. And A is minus T1 minus T naught divided by L times G, but G is set to be 1. And so now we have our slope and intercept of our straight line, and we can go back and say, therefore, our solution for the h equals 0 case is going to be T1 minus T naught is B, and then the slope is A minus T1 minus T naught over L times X, which we can write as T1 minus T naught times 1 minus X over L. This is the h equals 0 case. So we've done two cases. One is h is positive, in which case f was 0, and the other is h equals 0, which gives us this straight line. There's only one more to do for the first differential equation, and that is that h is a negative constant. So I'm going to set it equal to minus p squared. Again, p squared is going to be positive, so that minus p squared is negative. And so instead of minus h, we're going to have plus p squared f is equal to 0 for this differential equation. The solution which again you could confirm just by evaluating the derivative and plugging it back in, is a sum of trig functions. Okay, and like we've been doing, we're going to apply some boundary conditions. Actually, let's use the initial condition. So at all x, when t is 0, u is 0. The rod is at a uniform temperature of T naught. Okay, so if we take the x equals 0 case, putting in x equals 0, we're going to get cos of 0, which is 1, and sine of 0, which is 0. So f of 0 is just going to be a. So a g of 0 is equal to 0. Again, we don't want to put any restrictions on g right now. So a must be 0. Okay, we also have the x equals L case. At x equals L, we've already said a is 0. So we don't have to worry about the cosine term of f of x, but we do have to worry about the sine term. So we have sine of PL with the b coefficient, g of 0 is equal to 0. And so it must be the case that sine PL is 0. And so sine is 0 whenever its argument is an integer multiple of pi. And that means that there's lots of possible values of p for which the condition sine PL is equal to 0. And so we're going to add a subscript to p. And we'll use an n subscript. And our condition then is that p, whatever it is, it's an integer multiple of pi over L. And so then our solution, we got rid of the cosine term, but we still have a b, and then we have sine of PL, but now p is indexed by this integer n. Okay, so let's arbitrarily set b is equal to 1, so that what we end up with is n, fn of x is equal to sine n pi L times x. And so this is the h is negative case. Okay, so finally then we've done all three cases for the f differential equation. We still have the other one. Don't worry though, it will be less work. It'll be less work for a couple of reasons. One is it's only a first order equation, so ODE. And then actually we're only going to have to think about one of the cases. Let's just remind ourselves what that differential equation looked like. It's only first order because it only involves one time derivative. And we're going to think about only the h is equal to minus p squared case. And the reason we're going to do that is because when we thought about h positive, the result was that f was 0. And remember, what we're really trying to find is u, and u was f times g. So if f is 0, it doesn't matter what g is. So g of t doesn't matter. Okay. We also already saw that the h equals 0 case gave g was equal to a constant, right? We made use of that fact already. So in a way, we've already thought about that case. So all that's left is h is negative. H is minus p squared. So if h is equal to minus pn squared, and so remember from our f analysis, we already found that there was some condition on p, and so let's put that condition in. What we have to worry about is g dot plus, we're putting in a plus because h is minus pn, so the minus h becomes a pn, and then there was a c, and both p and c are squared, so we'll square them like that. Okay. So we know already that pn is n pi over l. We just worked that out. So let's say that pn times c is going to be n pi c over l, and we'll just define another quantity, lambda of n. Okay, and so if we do that, we got g dot plus lambda n squared, g is equal to 0. This is an easy equation to solve. You've solved this many times before. If we multiply by dt and divide by g, then we get the following. And the solution is, on integrating, we'll get the ln of g, and then we can exponentiate, and we'll put a subscript n on g because we already have a subscript lambda n. And so we end up with the following solution. Okay, so if we combine everything, the u was f times g. And so in the h equals 0 case, we got this linear function. This is h equals 0 case. And then we have plus, for h negative, for f, which was the time-dependent part, we had this sine function. And now we've just worked out that for the g part, which is the time-dependent part, we have a bn e to the minus lambda n squared times t. And we have to include all the possible values of n. And so we have a sum for all the different values of n that are allowed. And this is for h is less than 0. Okay. Notice that we still have a constant, this bn, that we haven't solved for. So we still need to determine the value of bn. We're going to use the initial condition. Okay, so the initial condition is that u for t equals 0 is equal to 0. And so when we put in t equals 0, the exponential e to the minus lambda n squared times t becomes e to the 0, which is just 1. And so then what we get is t1 minus t0, 1 minus x over L. The first term doesn't change, but then we have the plus the sum from n equals 1 to infinity of bn sine n pi x over L. And that has to be equal to 0. So now what we're going to do is we're going to use a trick. And you may have seen or recognized this trick from analyzing Fourier series. And so when you do Fourier analysis, or a Fourier series analysis, you make use of the fact that if you take a product of trig functions where you have this integer condition, and then we have two different integers, n and m, and we take that product and we integrate, that's going to be equal to L over 2, but only when n and m are equal to each other and we assume that they're not 0. Okay, so what I want to do is multiply u of x0 by sine of m pi x over L and integrate. Okay, so let's do that. Ux0 has to be equal to 0, so what we're going to end up with is I'm going to multiply by 2 over L and the sine mx. So we'll have a 2 over L. And then we're going to have the integral from 0 to L of t1 minus t0, 1 minus x over L, and then here's our sine m pi x over L dx. That's the first term. We still have the other one to do, and so we'll have a plus 2 over L, and then we have a sum, n equals 1 to infinity, bn, and the integral 0 to L of sine m pi x over L sine n pi x over L dx. Okay, now what we're going to do is we're going to say the second integral we have is the 2 over L and the integral of the sines, the products of the sines, that leads to the delta function. And so we have a sum of n equals 1 to infinity, and then bn are left over. But then we have the delta function, delta nm. And that's only 1 if m and n are equal to each other. And so this evaluates. Otherwise it's 0. And this evaluates to just bn. So we greatly simplified the second term, and we've in fact isolated this coefficient that we were looking for. We still have another integral to do, and what we have to do is we have to solve the following. It's the integral of some linear function of x times sine of x. And you may recognize that the way you should do this is by integration by parts. So we can solve this by integration by parts. So this is like the integral of u dv is equal to uv minus the integral of v du, and if the limits are between a and b, then you're going to evaluate both terms on the right between those limits. Okay, I'll let you do that for yourselves, and what you can do is you can confirm that the result is pretty simple. It's L over m times pi. So finally then, if we combine all of this stuff, let's see, we have 0 is equal to, we're going to have t1 minus t0, and then that integration by parts that we just did. So it's t1 minus t0. The integration by parts gives us Lm over pi, and then we still have a 2 over L out front. Okay, and so you can see what's going to happen. The L is going to go. And then the second one was just plus Bm. And so therefore, Bm is equal to minus 2 t1 minus t0 over m pi. So that was the coefficient we're trying to find. We used this trick from Fourier series to do that. And what we can do now is we can go back to our solution for u and substitute in the value for Bn. So we just have to change the m subscript to an n. And what we get is u as a function of x and t is equal to t1 minus t0, 1 minus x over L, minus, I'll pull out this coefficient that we just calculated. We'll pull out everything except the n, because that has to stay inside the sum. And so what we have is e to the minus lambda n squared t, and here's the 1 over n from the b coefficient. And then we have sine n pi x over L. Okay, we could write this maybe a little bit nicer. There's a common t1 minus t0 factor. And so what we get is 1 minus x over L minus 2 over pi sum n equals 1 to infinity e to the minus lambda n squared t. That entire exponential is divided by n, and then the sine n pi x over L. Okay, good. That's the solution, and it's complicated. If we want to get the actual temperature, remember what we did is we defined this U quantity to be T minus T naught. So we have to add T naught to everything. So we get T naught plus T1 minus T naught. And then just rewriting everything that was in the square brackets. Exponential minus lambda squared T over N sine N pi X over L, and close the bracket. This is the solution, and let's just remind ourselves what some of these quantities are. Lambda n is n pi c over L. C squared was alpha, And so that means C is just the square root of alpha. And then finally, alpha was the thermal diffusivity, which is the ratio of the thermal conductivity to the specific heat. Okay, we could notice a couple of things here. One thing we can notice is that the term with the sum is the only term that has any time dependence. The rest of the terms are independent of time. And it's a e to the minus lambda squared times t, a negative exponential. So if you wait for a long time, that negative exponential becomes really small. So after a long time, the sum of e to the minus lambda squared t term becomes negligible. Okay, so for t large, t of x becomes independent of time, and then it's going to be approximately just t naught plus t1 minus t naught, 1 minus x over L. And if we were to make a plot of that, if we put in x equals 0, then we have t naught plus t1 minus t naught, and it just becomes t1. And of course that has to be the solution, right? Because that's where we said that step in temperature was going to be. It's going to step up to t1 at x equals 0. Then if we put in x equals L, then we have 1 minus 1 in the last brackets, and we just get t naught. And so if t naught is over here, then what we end up with after a long time is just a linear temperature profile along the rod. So after a long time, the temperature distribution is linear in x. If we want to know what happens at some intermediate times or just after the step in temperature, then we have to use this whole solution here, and we have to do the sum. And the sum goes as 1 over n, so the terms get less and less important as n grows. So what I'm going to do is I'm going to try to show you some plots here for this solution for the sum truncated at n equals 500. So here's the conditions that I'm going to plot. First, maybe I'll say we can now determine the temperature at any position along the rod at any time. So for example, let's suppose we had copper. For a copper rod at about 10 Kelvin, the thermal diffusivity alpha is something like 0.1 meters squared per second, right? You go look up the thermal conductivity and the specific heat, and you could calculate its value. So if initially the uniform temperature distribution was 10 Kelvin, and then at t equals 0, at the x equals 0 position, we step the temperature from 10 to 11, let's suppose, and let's say our copper rod is 10 centimeters long. So what I'm going to show you are some plots of this function, our solution that we calculated. So keeping terms up to n equals 500, here's a plot for x equals 0.05 meters or 5 centimeters. So it's at the midpoint of the rod. And this is for times that are between 0 and 50 milliseconds. And so let's see if I can add this plot in. Okay. And so there it is. I'm just going to see if I can make it slightly bigger. Okay. And so we could check a couple things to see if it makes sense. Initially, the rod was at T0. And so that's what we'd expect at T equals 0. And then a long time later, it's asymptotically approaching a flat value. And if we're at the midpoint of the rod, and the temperature difference across the entire rod is 10 to 11, we'd expect the midpoint to reach ultimately 10.5, and that looks like where it's headed. Okay, so we could have plotted this for longer times, and we would have indeed found that we reach in equilibrium 10.5 Kelvin at the midpoint. Okay, the other thing we could do is we don't have to look at temperature as a function of time. We could keep time fixed. And so let's say 10 milliseconds. And we can look at how the temperature varies as a function of position along the rod. And so I'm going to add this thing in. And so here's our second plot. Okay, good. And so there is, again, we could check to see that this makes sense. At a position of 0, we expect the temperature to be 11. And that's the T1, and so that works. And then at a position of 10 centimeters, we expect the temperature to be T0, and that's where it is. And so here we see, after 10 milliseconds, what the temperature profile along the length of the rod is. If we made the same plot for a time that was much later, like 50 milliseconds or 100 milliseconds, what you would see is that eventually this curve would evolve to a straight line, and that straight line is equivalent to where is it? This expression here. And this plot here. Okay, good. So thanks very much. That's a solution to the 1D heat equation for a particular scenario. And as you can see, it was a lot of work to solve, and the solution ends up being quite complicated. Nevertheless, we can do it. All right. Thanks very much, and we'll see you next time.